This video is prepared by Avya Classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIMS and NEET. Hello friends, now we are going to discuss law of motion. Earlier we have learned about the motion in a straight line, motion in a plane, circular motion and other kinds of motion. Now we will learn what causes the motion or what is the reason behind the motion. So this chapter deals with all laws of motions. So first, to start or stop a motion, a force is needed, and whether to exert a force, touching is required or not. So this is the basic question, that touching is required or not for any force. So force can be exhibited with touch and without touch. So if I say that force with touch, consider the figure where a ball is hit by a bat. So or consider the collision between two balls. So suppose this second ball was in rest and first ball moves and hit it. So in this case the force can be exhibited with touch. Like here bat is putting some force on the ball to move it on, and similarly a ball of mass m1 hits a ball of mass m2 and imparts some force into it. So basically force can be exhibited with touch, it is quite clear to you, but force can be exhibited without touch, like gravitational force, electrostatic force. If you drop if you can see, if you drop a ball, you see that the ball moves towards the floor. So basically it's a gravitational force which is responsible for the movement of ball towards the floor. In the similar way, two similar charges repel each other and two opposite charges attracts each other. So these are the forces without touch. So it's shown in the three diagrams. A stone released from the top of building accelerate downward due to the gravitational pull of the earth. So suppose this is the earth or the floor, and if I drop a ball from a height edge, clearly the ball moves towards the ground. In fact, it accelerates, and it accelerates with an acceleration equal to g. Because of this, here if the velocity is less and it is supposed to 0, if I drop the ball, then it hits the ground with some velocity given by square root 2gh. So you may see that here initially there is no any contact between floor and the ball, still the floor attracts the ball. So this is due to the gravitational pull of the earth. So if I say that suppose there are two masses, one having mass capital M and another having mass small m, then these two masses attracts each other with a force given by the gravitational force, and gravitational force value is equal to gm into m divided by r square. So gravitational force always exists between two masses. However, it is not visible or it is not perceptible to us because of very less value of g. As g is having very less value, that's why these two body seems to be at the constant place. Third, I have shown the figure where a positive charge q1 attracts a negative charge minus q3. These two charges are placed at a distance r2. So if these two charges are placed at the distance r2, then the force experienced by this charge q3 is equal to fe3, and it is equal to minus 1 by 4 pi epsilon naught q1 q3 by r2 square. See, if you see that force is inversely proportional to distance square of distance between these two. So these two body are not in contact with each other, still they experience some forces for each other. And similarly, if I place a positive charge q2 at r1 distance from positive charge q1, then these two charges experience a force. Here the force is repulsive in nature. So how in the case of opposite charges, forces are attractive in nature. In case of similar charges, forces are repulsive in nature. And F E1 is given by 1 by 4 pi epsilon naught q1 q2 divided by r1 square. So you may see that these all kinds of forces in which they experienced without touching. In day-to-day life, we see that a bar magnet can attract an iron nail from a distance. You have already seen all those experiments in your school. So clearly force can be attracted, force can be exhibited without touch also. Now, first thing we have learned that force is needed for the motion, and second thing is that force can be exhibited with touch and without touch, both. Now the next question which comes in the mind of scientists, that is an external force required to keep a body in uniform motion. Suppose we move a body, so wherever the body will move in uniform motion without applying any force. So that's the question comes, that is an external force required to keep the body in uniform motion. And for this, first Aristotle fallacy comes in picture, and it says that the Greek thinker Aristotle says that if a body is moving, something external is required to keep on moving. That is, an external force is required to keep the body in uniform motion. What he says, that what he observed, that if I throws a ball with some velocity, some velocity v, then to keep this velocity constant v, an external force is required. However, it was proved wrong. Why it was proved wrong? Because if you see that if you see in the first glance, it seems to be true, as we need some force to keep this body in the uniform motion, otherwise the body will stop. However, they come in rest not due to they come in rest due to some opposing forces in the nature. Like if I throw a ball, then as soon as I start moving, as soon as the object start moving, it will have some external force which is called the frictional force between these two bodies, and because of this it comes into rest. And similarly, if a object is dropped in the fluid or in the air or any fluid, then there are some viscous forces always present in the natural world, and because of these forces the object comes into rest. So the object comes into rest due to some opposite forces, not by itself. So some external force is not required to keep in moving. If we counterbalance these opposing forces, suppose this is the ball which is moving with some velocity v, and the opposing forces F, that is frictional forces, are present here. If I counterbalance this force with some external force, then the object keep on moving. Or if I move the object on a smooth surface where the frictional force due to floor or the viscous force due to air are not there, then the object will continue to move with a uniform motion or with a uniform speed. So there is not any external force required to keep a body in uniform motion. Then comes the law of inertia. There was a great scientist called Galileo, and he made some observation on the motion of object on an inclined plane. So what Galileo observed? Galileo observed that object moving down an inclined plane accelerate. Galileo observed that if an object is moving down on an inclined plane, having some inclination theta, then it accelerates. An object accelerates. He also observed that if a object, if it moves up the inclined plane, then it retards. So if the object moves on inclined plane, it retards. And third, he observed that the motion of object in the horizontal plane is in between of these two situations. So Galileo concluded that an object moving on a frictionless horizontal surface, see, this is the frictionless, this is the frictionless surface, so there is no external force, no frictional force is acting on this object. So Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor retardation, and it should move with constant velocity. So it was the important concept which is deviation from the Aristotle fallacy, that a object which is moving on the frictionless horizontal plane, having no any opposing forces, moves with a constant velocity. And to understand this, Galileo did some experiments, and these are the experiments done by Galileo. That first is the Galileo take a doubly inclined plane. So it's a doubly inclined plane having one side inclination downward while on other side inclination upward. So one side it's upward inclination, one side it's a downward. So the object, when it moves from the downward inclination, it accelerates, and while in the other case, when it moves upward the inclined plane, it retards. So Galileo observed that a ball released from the rest of one of the plane rolls down and climb up the other. So here in this region it's accelerate, and in this region it retards. So Galileo observed that it becomes stop at some height. Galileo further changed the inclination, like he changed the inclination in such a way, keeping the height constant. So this is shown in this figure. He changed the inclination, and it was observed that the object moved to a more distance while the height remains the same. So if you see this figure also, the height raised by ball remains the same that the height from which it was dropped. However, the distance traveled by object is same. In the second figure, I may say that if I drop a object, then Galileo observed that although it moves a more distance, the height raised by object is same as the height from which it was dropped. So if the planes are smooth, the final height of ball is nearly the same as the initial height, a little less but never greater, because we are unable to make the whole system frictionless. So Galileo observed that if the plane are smooth, the final height of ball is nearly the same as the initial height. Secondly, what Galileo did, slope of the second plane is decreased. Here the slope of the second plane is decreased, and the experiment repeated. The ball will still reach the same height, but in doing so it will travel a long distance. I have already explained this. And again, Galileo what did, it just make other inclination equal to 0. Then he observed that the ball will move with a uniform velocity if we make a frictionless surface. So this is the observations of Galileo, that in the limiting case, where in the limiting case, when the slope of the second plane is 0, that is it is a horizontal, the ball travels an infinite distance.